For you physics geeks, July 4th, 2012 is a special day because on that day 4 years ago, I should say, scientists at the LHC announced they had observed the Higgs Boson. The hunt lasted nearly half a century, but the Higgs was only the tease. It filled in a big piece of the puzzle of understanding the universe, but gaping holes remain to be filled in the particle zoo. And this week, teams of particle hunters, one from the Large Hadron Collider in Geneva and the other from the Cube Neutrino Detector in Antarctica, reported that no, they have not found signs of any new particle. Bummer. Well, but the search continues. What exotic particles are physicists looking for and why? James Beacham is a postdoctoral researcher at the Ohio State University. He's also part of the Atlas team at CERN. He joins us from Geneva, Switzerland. Welcome to Science Friday.
Hi. Thanks. My pleasure.
Janet Conrad is a professor of physics at MIT in Cambridge, Massachusetts. Welcome to you, Dr. Conrad.
Hi. Thank you very much. I'm pleased to be here.
And if you don't know a neutron from a neutrino, we'd like to hear from you. Our number, 844-724-8255. 844-Sci-Talk, or tweet us at SciFri. Dr. Beacham, we have spotted the Higgs again after that first finding, haven't we?
Indeed, we have. That's one of the biggest successes of the last round of results that we released at this big conference last week. We did rediscover the Higgs, so this is fantastic news.
So that got a lot of folks at LHC excited about possibly finding some new stuff. This little bumplet they talked about that turned out not to be a new particle.
Well, yeah. In fact, it's been a bit of a whirlwind few months because of that little bumplet. But yeah, so that got a lot of attention in the press. The Higgs discovery is somewhat distinct from that, but this little diphoton bumplet, it was a suggestive hint of new physics that we announced back in December of last year. It turned out that at the time we pointed out this was not so statistically significant. A little bumps like this come and go in our field, but the kind of suggestive thing about it was that both us and the Atlas experiment and the CMS experiment, we kind of roughly saw the same little bumplet at about the same place. So the theory community sort of ran with that, and the news got in on the subject. And so there's a lot of this was the topic of a lot of attention. And so then we took about 5 times more data this year, and it turned out that the little slightly not so suggestive bumplet turned into a nice smooth line. So. That's no new physics there, but it's been a whirlwind few months.
Yeah, I'll bet. Dr. Conrad, you call yourself an anomaly hunter, and you specialize in neutrinos. But the neutrino is accounted for, right? I mean, why is the neutrino really interesting?
So the neutrino is one of the only standard model particles that has actually been behaving differently from the way that we actually predict particles should behave in the standard model. And we've already seen it behave differently. We have seen that neutrinos have mass when the standard model says that neutrinos should not have mass. So that leads you to start asking what other kind of beyond standard model properties would neutrinos have. And so that's why they're so interesting.
And just briefly, the standard model is the model that physicists accept to how the universe is made and all the particle zoo in it?
That's right. It's what describes the little particle zoo, but it's a model, not a theory, in the sense that we have to give it a lot of inputs in order for it to be predictive for our science, and we have to go out and measure those inputs. They're not coming from first principles, and so that's why we call it a model and why we think that there's a larger theory behind it.
That's a great explanation. The Cube Detector, that's in Antarctica, correct? That announced.
That's right, but I've never been to Antarctica.
I won't brag that I have. So we'll just.
It runs on its own, and then it sends the data back to us for analysis.
Well, it did not find. It announced that it did not find any sterile neutrinos. Now, what is a sterile neutrino? What were they looking for?
Okay, the sterile neutrino is a cousin that we think would exist to the existing neutrino. So theories say that there should be sterile neutrinos, and they give us a little bit of an idea of what those neutrinos should look like in our data. And so we go out and we try to look and see if we can see those features. And so it's kind of like if you were an explorer and you went out to a new world and you were looking for an animal, and you were told that animal is going to have one blue eye and one brown eye. And you go out and you look, and what we've seen in neutrino physics is flashes of blue eyes as we look around, but we've never seen the brown eye. And what IceCube did was a very thorough survey of this area and to try to understand if we ever see a brown eye in that area of parameter space. We never do. So this either means our sterile neutrino doesn't look like what we thought, our sterile neutrino knows how to hide its brown eye, or it's an anomaly that, like the little blip that was being discussed earlier, may actually go away.
With all this esoteric dark matter that we don't know what it's made out of, could this sterile neutrino be a candidate for some of the stuff?
Oh, yes. Sterile neutrinos are definitely a candidate for dark matter. The favorite candidate for dark matter comes and goes in my field, but right now sterile neutrinos are one that people are definitely considering. The sterile neutrino that we were looking for in IceCube, it has a little bit less mass than the sterile neutrino that people talk about for dark matter, but they would all be a related family.
And so you're not talking about the WIMPs, you're talking about neutrinos here.
That's right. A WIMP is something different. A WIMP is actually something which people usually associate. Well, first of all, a WIMP is pretty heavy. Yeah. And it's also something people usually associate with supersymmetry. And the sterile neutrinos are a completely different way of asking about dark matter. You know, it's because we haven't seen the WIMPs that we were looking for, we need to start thinking out of the box on dark matter, and this is one way to do it.
All right, let's think out of the blocks on the phones. Our number, 844-724-8255. Let's go to Deer Park, New York. Mark, hi, welcome to Science Friday.
Hi, appreciate you guys taking the call.
Thank you. Go ahead.
So, a quick question. I remember, watching documentaries in astronomy and physics about neutrinos and not really understanding it that much. But I got a quick question. Do neutrinos take up space? Like, so for instance, if you could put 1 million neutrinos in a jar, would you be able to put more stuff in there, or is it like light? I never kind of. Sorry.
Yeah. What are these?
Well, in a basic sense, the standard model is the description of the very, very small, like Janet was pointing out with neutrinos, and each one of these particles has a different a different mass, but this mass is not the same thing that we think of in terms of like a massive bouncer at a bar or something. The mass is sort of like a number that Mother Nature puts there for us, and so these particles are point particles to the best description that we have, and so they don't take up space per se. They have other properties, but they don't take up spatial extent. So you can put a large number of neutrinos in a jar.
So we would have 1 million neutrinos going right through us now, sitting here.
Probably more than that. Is that right, Janet? Yeah.
Go ahead.
Yeah, and in fact, we have, we have, as Jenna pointed out, we have a lot more neutrinos passing through our body right now every second. We also, by some estimates, we have something like billions of particles of dark matter also coursing through our body right now. And this would be some of these WIMP hypotheses and some other related, out of the box hypotheses. And so there's a lot of stuff going through us right now that we don't necessarily, it's not interacting with us. So. No spatial extent in that respect. Speaking
of a lot of stuff, Dr. Beacham, what exotic particles do you think could be floating out there in the universe that maybe the LHC could find, or maybe we need a bigger machine?
Well, that's a really good question. What I think doesn't really matter. Mother Nature chooses, for us and our job as explorers is to go and look for it. So. The things that we're looking for and we're sensitive to at the LHC are, for instance, we can't actually look for dark matter particles. We can't directly detect them because they're dark and they don't interact with our standard apparatus, and so we have to detect them in indirect ways. But yeah, dark matter is something that we look for at the LHC. We're also looking for things like exotic heavy cousins of the Higgs boson. And we're also looking for things like gravitons. And this would be a hypothetical particle of gravity, which has been theorized for a very long time, but we've never seen an evidence of.
Mm-hmm. And Janet Conrad, you're working on a liquid argon neutrino experiment. How would this work differently than the other neutrino detectors?
So this is a new state-of-the-art technology, and it's 170 tons of liquid argon. Liquid argon is about very close to the same temperature as liquid nitrogen, so it's a cryogenic experiment. And the reason why you use it is because you can actually get exquisite images from a detector like this. So it is almost like you're looking at a photograph of the neutrino interaction as it occurs. It's very exciting. It is also very state-of-the-art, and so we are in the process of trying to bring up our detector now. The first big one, the really large one to be built in the United States, is Microboon, which is running at Fermilab.
Well, let's go to the phones. A lot of questions here coming. Let's go to Savannah, Georgia. Hi, Mitchell.
Hello, how are you today?
Hey there. Go ahead.
Yes, I was curious. I've heard a lot of talk about the LHC recently and other super colliders all around the world. And many scientists, such as like Stephen Hawking and others, have come out and said that it's very dangerous and you're basically playing with fire. How do we know that these are actually safe and they're not affecting our weather or our electromagnetic sphere that we have, the magnetosphere around the Earth?
Mm-hmm. James, Janet, who'd like to tackle that one?
Well, I can speak for the LHC. The notion of the LHC, we talk a lot about how we are exploring the unknown here with this highest energy ever, and that highest energy ever is something called 13 TeV, trillion electron volts. And this really is the highest energy that we've used in a collider experiment. However, this is not the highest energy by any stretch of the imagination of even things that happen nearby us on the globe. So, for instance, there are particle collisions that happen in the upper atmosphere from incoming cosmic rays that are thousands of times more energetic than our collider experiment. The whole point of our collider experiment is that you take protons and you accelerate them up to almost the speed of light to this 13 TeV, and then under very controlled conditions in a laboratory, you have a beam where you collide those like 40 million times a second, something like that. Mm-hmm. So the energies that we're actually using for a single proton at such high energy, it may sound, it is impressive in terms of laboratory and pushing into the scientific unknown, but it's kind of it's actually the kinetic energy of, like a mosquito. So it's not such a big deal. In the magnetic fields that we use in these magnets, we do have to keep our magnets in the LHC tunnel. We have to keep them at very, very cold temperatures, actually colder than outer space, so that we can bend these protons. But the magnetic fields that we're using are really, really insubstantial compared to the larger ones. So it's an extremely remote possibility that we're affecting weather patterns, and no one's ever seen any evidence for it. So I think you're okay.
Let's go to Steve in Killingworth, Connecticut. Hi, Steve.
Hi. Got a situation for you and a question. Suppose I was going to study a bowling ball, and it was in this dark room, and the way I decided to study it was to shoot another bowling ball at it and bust it all apart. The only thing I could look at was the remnants of the pieces of this bowling ball that blew apart. Wouldn't that give me a rather strange interpretation of what the bowling ball was? And my question is, isn't there any other way to study these minute particles and waves and energy than blowing them apart?
Let me get Janet to answer that first. Janet?
I think that's a perfect analogy. That's an example that I like to use is actually that you hit an egg. So you throw a BB at an egg and you blow the egg apart. Would you then be able to reconstruct that back into what an egg actually looks like? We've had to work really hard in order to be able to understand how to go backwards and put together the picture. So there's ways that we can do this. We can hit it with a lot of different things and understand how the debris behaves. But unfortunately, when you get down to these very, very tiny scales, you really have to blow things apart in order to be able to really understand what's going on inside of them. We haven't found a way around that.
Yeah. Is it more exciting to find what you're looking for or to find something that you're not looking for?
To be honest with you, for me, I'm really excited about this IceCube result because it was not actually what we expected. And it's very hard to put this together with the other data that's out there that says that we should be seeing sterile neutrinos. So I see this as a real opportunity to go on another expedition. So I am really happy about it. I realize that it's hard to explain that to the world, but it clearly is a great thing to find the thing you were looking for. And so, the folks at LHC, I can't imagine how excited they were when they saw the Higgs. Mm-hmm. It has to have been great.
This is Science Friday from, let me just interrupt rudely. This is Science Friday from PRI, Public Radio International. Okay, James, go ahead.
Yeah, no, I was just going to say I totally agree, and we were over the moon when we discovered the Higgs boson, and but this was the last remaining piece of the standard model to plug in, this puzzle piece, and beyond that, anything we find beyond that is going to be completely revolutionary, because it'll be the first evidence that we've seen of a fundamental particle outside of this wildly successful standard model. And so it's a really good example to have both of these experiments on at the same time, because we both published kind of null results in a sense at around the same time. And the message from the LHC last week was not so much that just this little diphoton bumplet faded away. It was more that we have just reported our first initial findings at this kind of, I think of it as like, an alien planet, 13 TeV. We don't know what we're going to find. We have, probably 2 decades worth of research to do on this data, and we just barely got here. So it's like it's our job to, report back to home base in a sense. If we go to an alien planet, we look around very instantly, see if there are any big fuzzy easy to spot monsters. We don't see those, and so then the next we don't disappear immediately. What we do is we spend the next decade to 2 decades combing through the sand trying to find the hidden stuff that could be there. So for me, what this demonstrates is that we didn't see any easy to obvious to spot particles. So this this motivates the next 10 to 20 years of research, and then possibly a larger collider in the future.
Janet, there is a group, I understand, looking for milli-charged particles with lasers. Tell us what that is.
Oh, yeah, this is a very interesting piece of work, which is being done a lot out of Stanford. And this group is looking for particles. So at the moment, all of the particles that we know of have integral charge. They have 0 charge or 1 charge, or maybe 2 or more, but they don't have fractional charge that we are able to actually see in the outside world. And so these people are looking for milli-charged particles. They take little balls and they balance them on laser beams. And if you have a tiny little extra bit of electric charge on them, it would cause the balance to be off. And so they can actually search for this. So it's neat. It's tabletop physics. Literally, it's on a laser table that is addressing questions that are really high energy scale questions in physics.
Wow, we'll have to watch for that result. Thank you. That sounds like kind of fun.
It is a really neat experiment that these people are doing.
All right, we're going to follow that. Some more. Janet Conrad, professor of physics at MIT. James Beacham, postdoctoral researcher at Ohio State University, also part of the Atlas team at CERN, joining us from Geneva. Have a great weekend. Thanks for taking time to be with us today.